go to question 26. And we have 2-point charges plus minus q, distance d from each other, magnitude of the electric field strength midway between the charges. Okay, so it's always best to draw a diagram in these cases. We have q, and we have negative q. Okay, and let's take an arbitrary charge. Let's take it as q. And so this distance is d. Let's actually put the distances somewhere here. This distance is d over 2, and so is this. So we have, so if both of these are positive, right? Positive, positive. We know, let's draw the forces. Positive charges are going to repel. So q is going to move to the left, and tiny q is going to move to the right. Just looking at these two. Now if we look at these two, this is negative and this is positive. So these are going to attract. So then there's going to be another force this way. Actually, let's write it like this, right? And then let's use green. So there's going to be another attractive force this way. It's going to be the same size because both are the same charge. And Q is going to have attractive force this way. So we have to sum both of these up. And so you can instinctively tell that it's going to be an increase or a positive, so it can't be 0. It then comes down to the formula. And so the formula we know is F is equal to KQ R squared. And R squared is D over 2 squared, right? And so this is the same for both charges, this and this. But we know we have to add them, not subtract them. So we have two equal forces on this arbitrary charge in the middle. So we have 2 times, that becomes 4. And we have 4 come up and d squared down. Right? You see where I get that from. This becomes 4, and then it comes up. And we have 8kq over d squared. And looking at this, we can tell it's just this. And so actually where we lose tiny q is when we use the electric field strength formula, which is just E is equal to F over Q, which is equal to A. But you don't really need to do this when you're under timed conditions in an exam. And the Q comes out. Right?